As will happen to all of you at some point in your professional life, Microsoft has decided to update the laptop in a serious way. And this is again something that you will have to look forward to in your professional lives. Understandably, it's not practical for AMD to allow free access to its corporate data, right? So a lot of the data, things like this presentation, isn't trivially available. However, while the team over there is just fixing things fairly shortly, I'm sure all of you have at least come across the phrase AMD. The company's come a very long way from being a second source supplier of Intel CPUs. This was back in the day when the US government required to purchase a semiconductor for a government program, they would require there to be at least two companies manufacturing it.
Just to share.
So AMD partnered with Intel to become the second supplier of the processors. And after that, it's actually been quite a long history. I am an early adopter, I guess, of non-Intel CPUs, mainly on cost reasons when I was at college. I even had something from a company called Citrix, which doesn't really exist anymore. But also, AMD famously innovated in a moment when Intel were trying to introduce 64-bit computing, but they wanted to introduce a completely different 64-bit computing design. And it was very, very slow to get to market, and it didn't actually function very well. AMD, however, innovated around the existing design of the Intel instruction set, making a 64-bit version and correcting some of the deficiencies of the 32-bit system. And it is so dominant that even now the variety of Linux I run on my laptop is labeled _AMD 64, because Intel then licensed and had to license AMD's design to continue making their own processors. Oh, it looks like we might have some success. In that case, let me just cut across to the laptop, hopefully. There we are. Sure. And in this particular case, I'd like to take the opportunity to introduce Andrew Schmidt. He's here from AMD, from the university program, but also having a deep experience of the semiconductor industry before joining the university program, and who's going to be talking to us about how AMD is applying AI within its high-performance computing group, which is kind of very cool. So, yep. Andrew, thank you very much.
Excellent. Hopefully everybody can hear me all right. I appreciate it. Thanks everybody for your patience as we're getting this system rebooted over here, but luckily my colleague Scott brought another computer, so we have some redundancy. So I'm going to talk a little bit about AMD, my experiences, a little bit of my background, just kind of how I got to where I am, and then we'll talk a little bit more about AI and some of the different technologies that we have available. And then hopefully we'll have plenty of time at the end for Q&A. I have to put in the typical disclaimer that no matter what I say, don't hold it against AMD. It's not their fault, it's all my fault. So this material is largely on my own, but blessed by the company. So the quick agenda that I have here, I'll give a little bit of motivation of kind of my background, why I became kind of who I became, which may be relevant for a lot of you. I think just quick show of hands, are most of you like at the freshman or sophomore level? Is that kind of cool? So I'll kind of explain kind of where I was in your shoes many years ago and kind of what then led me down to the path to where I am today. That includes a little bit of the academic background, some of my work experiences, and then kind of conclude a little bit more with what AMD is and what's interesting there. So to begin, I would say that one thing I'm very curious. I really like to learn how things work. Much to the chagrin of my parents, I took things apart as a child. I would imagine most of you probably are in that similar category. How does it behave? Why does it work the way it does? I will admit I never was as organized as the picture shows there. When I took things apart, it was a scattered mess, and yeah, maybe sometimes it did get put back together properly, but often not. When I kind of went from being in that curious state to becoming more of a tinkerer, somebody that was, okay, can I try to build this, or can I modify it or manipulate it in some sort of form or fashion? It's kind of the next evolution of that, how does it work? Why does it work? What can I do to maybe improve it? And once you kind of get into that tinkerer mindset, for me, it really led me down to the designer mindset of, okay, now that I understand how these things behave and work, maybe the smaller components, what can I do with it? What should it do? What are the requirements? What are the specifications? What's my budget? And really starting to push me into more of that, the engineering mindset of problem solving. So hopefully a lot of you have maybe similar questions that you think about, things that you find either you're curious or you like to tinker, you like to play around with things, or you're really interested in the design side. And it doesn't have to be about computers, electronics. It can be about AI or machine learning or something completely different, semiconductor related as well. For me, a couple of different courses that really were impactful in my career, kind of solidifying who I became and what I wanted to do. The first was digital design. So I don't know how it is exactly. I'm not a Purdue alum, but when I started in my undergrad career, we were told C, C++, got to learn how to program. That was the first step. So you're sitting there trying to get something to work. At the second semester, we took digital design, and it was the first time we really got to kind of touch hardware. We got to actually solder things, wire wrap things, build different circuits, and it was that realization of kind of turning that logic, these ones and zeros into something functional that really kind of started to really pique my interest and inspire me that, hey, we can actually do something, and it really exists in the real world. From there, I started to learn the differences between like synchronous circuits and asynchronous circuits, things like memories and clocks, finite state machines, how to actually start to build things that will run eventually these computers and these processors that we have. How do you describe these different circuits? Yes, you can do these gate level designs and AND gates and OR gates and everything, but there's much more efficient ways to describe that, harder description languages, and being able to kind of talk about the syntax. So it was with digital design that I was like, oh, this is really maybe something that I could be good at. I did terrible. My undergrad C, C++ class, I think I got a C. It was just like, wow, I am not a really good programmer. But when I hit digital design and everything from that point on, computer architecture, it was like, okay, now I know kind of where I want to go. From that, right around the time that I finished that digital design course, I had a professor that I was talking to who told me, if you really like this, there's this new course I wanted to teach called reconfigurable computing. And it was rather new at the time. It's probably something that you're all probably hopefully familiar with a little bit as you go through your careers, using field programmable gate arrays. This is programmable hardware that you can change the functionality based on how you write the code for it. And it's different than a fixed CPU where you have instructions that decode and execute. This, I can actually customize that hardware functionality to do an image filter or some sort of video processing pipeline, some sound recognition. You can really start to make hardware do what it is you want. Your limitations largely are your own skills, and then how many resources you have within the chip. So I started to kind of play around with that and really kind of found that reconfigurable nature was really exciting to play with. One thing I wanted to highlight here is in reconfigurable computing FPGAs, you probably maybe even use it in your digital design courses now, hopefully. The usefulness for you all will be that you can use it in prototyping and also in verification. So I kind of call it like an FPGA sandwich where you start out and you're trying to design something and you might specify that circuit and functionality and then emulate that or get that functionality working on an FPGA. Then you send it to tape out. So this is kind of where maybe it's more relevant to like the semiconductor side of the house here in your VLSI design. And then when you get the chip back, you got to test it, make sure that it works. So you may end up using FPGAs to also be a test harness to then actually interface with the different circuits and chips to make sure that it actually worked. And the last thing I put up there was it's also useful for like low volume. So if you don't need to have hundreds of thousands or millions of these chips, you might just use an FPGA because it's just going to get that small number of inventory that you need out. But after I took the reconfigurable computing class, we had to do a senior capstone, which is like a senior design class. I'm sure there's like different variations that are done here. This to me was really exciting because it's a chance you get to put it all together, all the different knowledge, all the different experiences that you have throughout your curriculum. And for me, what was really interesting is it was starting to build a team where you have people that are strong in one area and not so strong in another area. So I was a hardware designer, so I was the one who was making the PCB design, was soldering all the components together, was really kind of specifying the hardware, getting the power design, power delivery mechanism, all that stuff working. And then I had a whole different team or teammates that were working on the software stack, so getting Linux, getting all the device drivers, all the code running and compiling. And we had to learn kind of how to work together so that they could run their applications on my hardware. That forced us to have to do project management, have to talk about schedules and dependencies. We learned about Gantt charts, which if you haven't done Gantt charts, you will, and it's really, really powerful tools for us to figure out like, okay, whose fault is it that we're not done yet? And then you kind of move on. After I completed my senior capstone, I was talking to some professors, and they were like, if you really like these types of different projects, you should consider grad school. And not knowing any better, I was like, okay, well, what is this grad school thing? I'll give it a go and try it out. And I found that for me, it gave me a chance to really dive deep and become more of an expert in a particular topic area. And the first topic area that I kind of looked at was something that was focused on the memory wall. So if you're at all familiar with computing, some problems are compute bound, where it's just like, if I could throw more compute resources, more processing capability, I could solve that problem faster. And there are some things that are just memory bound. It says no matter how fast my processor can run, I can't get the data fast enough, and it's starving. So that memory wall, that memory limitation, forces us to figure out different ways to create different memory hierarchies, different caching structures, different access patterns that allow us to actually feed that computing beast. So I took that as a challenge for my master's, is like, how do we design these more complex memory hierarchies to solve these challenging problems? And then I went one step further in my PhD. I had an opportunity to actually build a whole-scale high-performance computing system. So here's just an example of the cluster that we assembled and built, where we were stitching together different compute resources, and we had to literally do everything from like screwing together every single one of those boards, design custom PCBs, all the networking wiring, all those wires. There's probably somewhere on the order of 512 wires that probably on every couple months I got to go and change which wires were connected to which wires, which is way more efficiently done now with like different networking topologies. But that gave me a chance to really dive deep into that kind of area of expertise for high performance computing. I took that one step further and I joined the University of Southern California when I graduated with my PhD, and I joined their Information Sciences Institute, which is sort of the research and development branch of USC. So they do a lot of applied research. And as kind of a project lead, it was my job to propose ideas and then try to get funding and then go off and solve those problems. And the favorite place that I like to work for was DARPA, which is basically the Department of Defense. They would come to you and say, there's this really hard problem, and we'll give you a bunch of money if you can solve it, but we're not asking you just to do 10 times better or 100 times better. It's usually 1,000 times better than the state of the art. And so it required us to really kind of plan and dig deep and come up with really novel, interesting solutions. And I have a couple of examples of different projects, but I largely focused on hardware software co-design. So where do you take an application and you map that into, say, a hardware processor or an FPGA, or where do you run in software? How do you make systems more resilient so that if it is, say, under attack, or there's a radiation event that causes bits to flip and the system to shut down, how do you recover, make sure that it still is functional? We built lots of different prototypes. We spent many late nights, lots of coffee, trying to figure all these different things out, using a lot of the skills that I learned from early on of debugging and testing in order to kind of overcome a lot of these different problems. So a couple of examples. The primary one I focused on was something called hardware assurance. And I think that's something that hopefully you all can continue to help us solve, because this is an incredibly challenging problem. When you go out and fab these different designs, there's a non-zero probability that some part of that is not going to work. And it could be a design failure. So, the designer, Andy, I put a bug in, I didn't realize it. Okay, well, we have to figure that out. It could be a manufacturing issue. So as you go through this course, you're going to learn that it's not as simple as just, taking a chip and putting it in a socket and it all just works. You're literally going to go and you're going to fabricate these wafers, and you're going to see how complex these recipes. I mean, I literally feel it's like baking. Sometimes you get it right, sometimes you don't get it right. And so you need to kind of understand what caused those failures. And for me, what was really interesting is we needed to make sure that it was not just somebody doing it, like, oh, I was a designer, I put a bug in. There's situations where somebody may want to put that in to cause this hardware to fail predictably. And we needed to detect that there were no kind of like kill switches effectively in our hardware, because especially for like the Department of Defense, they want to make sure that the hardware that is deployed is going to function as expected throughout the lifetime of that part. So a lot of what we had to do was designing resilient systems. We try to approach this by developing different tools that would allow us at different points in the whole flow to be able to inspect what is the state of that design, be able to run a lot of different analysis. There's a lot of software development, even though we're hardware designers, but we were running a lot of different tests and trying to understand, could we catch and detect these failures early on in that life cycle? For maybe the rest of this kind of focus area, hardware-software partitioning, ASIC design, third-party IP, that part of it was a lot of understanding somebody else's design and how that behaves. We're not experts at somebody else's implementation, but if you're going to test to make sure it's functional, you now have to start thinking, well, what corner cases do they not account for, and start having to test for that. So we'd go off and run and do that. One of the areas that I really enjoyed right when I started at ISI was designing different test circuits to make sure that what you're designing was functional. And what we came up with, which is now kind of pretty standard, is we're testing these things at the component level. So we simulate, we make sure that the individual building blocks are functional, and then we take a bunch of those different building blocks and we build a full system. We simulate that full system. We take that whole system and then we emulate that. We run that on the FPGAs, or we run that somewhere in hardware where we can run lots and lots more test vectors at orders of magnitude faster. And then we send that chip off to get fabricated and taped out. And when it comes back, we run the same test vectors and really try to make sure that that function and behavior is still there. We did that on a number of different designs. One that I enjoyed working on was something called fully homomorphic encryption. There's a lot of different kind of techniques for this, but basically the idea is you want to be able to calculate and process on encrypted data while the data stays encrypted. So right now, if you're using your computer right now, you're working on unencrypted data. If somebody looks at it, grabs that data, they would be able to tell what it is you're working on. In this case, what we're actually able to do is encrypt the data, send it over to a machine that could then do whatever processing needs to be done on it, and then send the result back still in an encrypted form. This normally takes hundreds, if not thousands of times more processing time, so it's literally thousands of times slower than if you did it unencrypted. We needed to accelerate it, so we created different circuits, designed a chip that could try to speed that up. And this was a DARPA hard problem where they said, look, it's about 1,000 to 10,000 times slower than conventional. We would like it to get within 10x. So we had to work very hard to come up with different testing infrastructure to be able to do that. The last one I'll talk about before kind of switching gears over to kind of what AMD is, we got to work on a lot of different NASA kind of Earth missions. I was in the Washington, D.C. area, so we were very fortunate to be really close to Goddard Space Flight Center. A lot of the Earth scientists that work for NASA are at that facility, and they're constantly flying satellites trying to figure out what's going on in the Earth. And they were realizing in order to be able to do the types of processing that we need to be able to do climate change analysis, air quality, ocean health, ecosystems, all these different problem domains, we need a lot more processing capability. And it used to be that we would just grab all these samples and then downlink them as we were flying over downlink stations, as our satellites would flying around, and you'd downlink the data, and then a week later you'd be like, oh, there was a forest fire over there, and you're like, well, obviously, like a week later I know that it was there. What we wanted to be able to do was to detect that forest fire as we fly over, download just that one piece of information and get it computed. So we had to come up with different computer architectures that we could actually assemble, build, fly in orbit. So one of the fun things we got to do was package up something and it get bolted on. It was actually on a pallet that gets bolted onto ISS, the space station, and your flight experiment is flying in space, and you're communicating with it, and you're getting live downlinks back telling you that your system is behaving. For this particular test case, I was really curious about could we do image compression and reduce the amount of data that we were downlinking by orders of magnitude so that we could get the data down faster. And then also, if there were failures, there's things called single event upsets. So like these bits are flying around and they may cause the hardware to not behave as you want. Could we detect it and could we correct for it? So those are some of the different fun things that I got to do while I was working kind of between my PhD and joining AMD. At AMD, hopefully everybody knows or has heard a little bit about AMD besides the great intro at the beginning, but we're a high performance and adaptive computing company. We do solve really complex, challenging problems, and we have really great technology, which I'll kind of show a little bit about that. But within that, I work for the AMD University program now, and my charter is really to go to universities to work with students and faculty to really work with your education and research to help you do the next amazing things. So for this case, I'm going to challenge you here throughout the next few slides of some of the challenges that we're facing at AMD, but also globally across all the different challenges with AI and everything. I go to educators and I go to researchers, and I work with them to figure out like what's a barrier, what's causing you friction from being able to do the research, and how can we help. And I apply a lot of the skills that I've learned over the course of my career to help them. At AMD, we have a lot of different innovation. It's quite amazing to me to look back at the history of what has been developed, even over the last 10 or 20 years, not only at AMD, but the whole industry, and see what advancements have been made. Some of the ones I want to highlight here that are probably relevant to this group, process technology. We are a fabless semiconductor company now, but we care very deeply about how we use the different process nodes and the technology to be able to squeeze every last bit of power and performance out of those systems. So we have to know all the things that you're learning very well in order to be able to apply whatever design rules that we need or verification, testing, checking, and eventually all the way up to our software stack to make sure we're taking full advantage of that hardware. Some other technologies that we've leveraged are 3D die stacking and chiplets. So this ability to implement the technology in the right process node that's cost effective. So it may be cheaper to implement memory in a different process node than our high performance computing compute accelerators. So now we have the ability to manufacture those in different chiplets or different little parts and then stitch them together. And I have some animations I'll show you on how we kind of do that, which is fun. It's like Lego, but on steroids. So pretty neat there. And then the challenge that I really think that you all are hopefully going to help us address as we go forward are things like energy efficiency. You've probably heard that we are partnering with like OpenAI, and we have 6 gigawatts of compute that we're looking at. But like 6 gigawatts of compute, it's a terrifyingly large number. Gigawatt, right? It's a big number. There are ways to just add more hardware to go faster, or there's ways to maybe save a little bit of that power by implementing a different process technology. So if you are able to save 0.1% or 0.01% power, but we multiply that across 400, 500 billion transistors, that all of a sudden starts to stack up. And then when you take that across 100 or 1,000 or 1,000,000 of these devices, you can start to see some of the prospects for some efficiency gains. I'll touch this really quickly that, from a compute side of things, if you're not familiar with AMD, we cover everything from embedded systems, the low level, all the way to the cloud, AI. Hopefully you've all at least seen our processors. You're probably more in sort of that PC category, the second column. So the laptops that you're all using or the workstations that you have access to, hopefully are all AMD CPUs. But I wanted to also highlight here in the next few slides that some of these CPUs are becoming a lot more than just a general compute unit. Obviously, you can play games, you can do a lot of the different homework assignments that you have with it, but you have a lot more at your disposal. And so on that end, we have kind of 3 different categories that we'd like to kind of highlight. Typically, we have our CPUs, our central processing units. Those are our general processors, and they're pretty good at a majority of our tasks, right? Like your day-to-day things are going to be pretty sufficient at it. And we can parallelize those by having multiple cores that can be off and running on different tasks in parallel. Great. Hopefully, that's something that you're all familiar with. Our GPUs, our graphics processing units, which are now really just AI processing units to some degree, they're very good at a smaller set of instructions, and they can just crunch through those because they're doing so many of these operations all in parallel. And we could take it a step further and use something which we call our NPU, or our natural language processing unit, which is much more focused on AI processing. So now we're looking at even smaller bit precisions. We're really specializing what types of computation are we able to do, convolutions, matrix multiplications, and we're accelerating those components. It's not going to be good at doing a lot of the normal processing that your day-to-day tasks are. That's why we have a CPU. Or if you're needed to do graphics processing, well, you have a GPU for that. So now our NPU is really more geared towards a lot of the AI inference workloads. And what's really cool at AMD is we have all these different components. We can stitch them all together. In this case, this is our Ryzen AI socket, which has our CPUs, our GPUs, and our NPUs, these 3 different boxes, all on one piece of silicon. So you can imagine now you have kind of at your disposal, these are on the order of a couple $100 processors that allow you to do a whole wide variety of different applications that I would encourage you, if you're like, I don't want to do anything related to software development or programming, I get that. but you might want to experiment with some of this technology just to familiarize yourself with how different hardware is developed and then how software interacts with it. So a simple example, this is kind of put together by somebody, if I can get to the next click. Oops, one more second. So all things AI, you have to do a cat in a hat, whether or not you know or not. But our software is able to generate these images just based on a text prompt. Now this is pretty standard. You can go online and do this pretty easily, but this is all running locally on this local workstation. You can then complement that with doing, say, background blur detection if you're doing like a Teams or a Zoom chat, and you can start offloading a lot of the computation that would normally be running on a CPU, running on this neural processing unit. So again, just kind of simple examples of just with a few lines of code, you can go off and use these different compute resources. And what I wanted to, again, touch a little bit on was the software stack that is involved to do this is becoming a lot more sophisticated. It's a lot more accessible. We're trying to make it a lot more open source and available to you all. So you can go online right now, and there are a ton of YouTube videos and trainings and tutorials, things that you, again, may not think about. How this is a semiconductor class, like why would I do anything with software? At the end of the day, your hardware is only going to be as successful as your software. We've learned that quite well at AMD, and we're working really hard to improve that. So we want to make sure that you all are aware that no matter what you're doing, understand the bigger picture, who's the user of this technology, and try to make that as frictionless as possible. I won't go into a lot of detail about how you can go through and Hugging Face and download models and all that stuff. We normally have like hour-long tutorials on this, but for the interest of time, I just kind of wanted to highlight that. I also wanted to highlight, there are like just getting started applications you can download today and be running these large language models directly on your laptops or on your workstations, and you can start to develop different applications that will help you in your career and your education. One we literally just released a couple of days ago. It's built on Lemonade, so that one on the left, and it allows you to have a large language model that's directly coupled with GitHub. So if you go onto GitHub and you were to say, I'm going to clone this repository that I've never ever seen or heard anything about, you can start to interface with that repository as if you're using ChatGPT, and you're doing it all locally on your workstation. And where that's really powerful is you're not limited by the number of tokens that you have access to. If you've ever used ChatGPT and it's like, okay, you've run out of tokens, try again tomorrow, like, oh darn it, or you have to pay a bunch of money to go off and do it. Here, instead, you can be running it nearly infinitely just based on the model that you have and the hardware you have available. So I wanted to highlight that. I wanted to spend just a few minutes on some of maybe a more relevant computer architecture that we've been developing before turning over to questions, one of which is our Instinct line GPUs. What I find really fascinating about this isn't just one chip, it's many chips with many different technologies that we've been developing over many years. In fact, since about the mid-2010, 2012, we started to put together this idea that we wanted to build the world's fastest supercomputers. We wanted them to use our CPUs, our GPUs. We wanted scientists to be able to solve the world's most challenging problems with our hardware. So over the last 10, 12 years, we've been working very hard, and now we have the number 1 and number 2 top supercomputers in the world that use our hardware and technology. Well, it's question of like, well, how do you do that? It's not just like one day you're like, well, I'm going to make a bunch of these and I'm just going to put them into a rack and it'll just work. You have to really kind of start from scratch, looking at the computer architecture to figure out, well, again, what should run on the CPU, what should run on a GPU, how do they communicate, how do they interface with memory. So we looked at all these different permutations, tried to figure out what the right technology should be. We looked at what fundamental limitations were there for us to be able to achieve this. We had to develop new technologies, hybrid bonding, to be able to actually take and stack multiple of these dies together. We had to look at different ways to package all these different chiplets together to get them to be actually able to communicate. We had to figure out ways to have them communicate over very short wires without any interference or causing any disruptions. And what that allowed us to do, and I'll kind of jump through this a little bit, is create these different compute resources that we can stitch together. So we have our accelerators, our high bandwidth memory, and I'm kind of interested in time, just plop through this one real quick, and create what has now been released as our Instinct series. This is our 300A. So the differences in the 300X, MI300X versus 300A, is we can stitch together these different compute units that have general purpose processing. So domain scientists, they want to be able to still do kind of conventional processing, but they also want to use the GPU for acceleration. What I find really fascinating is that isn't as simple as, oh, I'm just going to write some code and have a couple of these blocks and then go tape out and come back in a couple of months and have a chip. You have to start out with this kind of silicon interposer, this base layer that you're going to now stitch together all these high bandwidth memories. And keep in mind, these high bandwidth memories, this is memory that's three-dimensionally stacked. So it's not just one chip, it's a sequence of chips that are stitched together. Those are then directly connected to kind of our I/O dilets that allow us to talk to all these memories and be able to access different vaults within that memory in different ways. And on top of those, we stitch together either our compute accelerate dies, or we can stitch together our conventional compute dilets to actually realize that physical silicon hardware. So the things that you're designing and developing, we will take, chop up in little chiplets, and then stitch together into these designs. As a kind of a whirlwind view, a little bit of some of what we develop and how we develop it. I wanted to also show one other picture that I thought was really neat to see. This is a cross-section view of our chip. Again, you're going to probably see these in your course as you go through this over the next few years, but maybe not to this level of sophistication. But just see how sophisticated, how detailed, we have to be very precise. So all the things that you're going to be learning, yes, it really does matter if you're off by an angstrom or you're off by a few micron. Your channels aren't going to align. What if you don't have the right cooling solution on top? Well, your chip is going to melt. So all these things are quite critical. I kind of mentioned a little bit already here that we can take these different chiplets, and what's really neat about at least how we've approached the problem is we can grab 4 of one and 6 of the other and create our MI300A, or we can say, look, we don't need the chiplets, the compute dilets, we're just going to put only the accelerate dilets in there, and we're going to create our MI300X, which is like our big chiplet we sell lots of and make lots of money on. Or we can not include any of the accelerate dilets, and we can just put the I/O dilets and the compute dilets, and we can create our server grade chiplet devices, and in this case our EPYC CPUs. That ability to shuffle around what resource gets placed where allows us to really kind of hyper specialize what the solution is that our end customer will end up needing. So that was a really fast survey of some of the different technologies that we have available. I did want to highlight, because we do have some of our team here, we have a really amazing intern program. This are a little bit more geared towards that 3rd and 4th year, and we had just a really great session right before this. But an internship is a fantastic way for you to learn, what is AMD doing, and is this a good fit for you? A lot of the times, and I'll let maybe some of my colleagues that are here during the Q&A session maybe be able to talk to some of it, but it's an opportunity for you to try out and see how our technology is working, but hopefully also be able to contribute back to a lot of the different projects that we have that we need you all to come out and work on. There's a lot that you can learn from that. I probably won't spend a ton of time really highlighting that. Instead, what I wanted to kind of wrap up with was just a couple pieces of advice. The first really want to emphasize is for you all to stay curious and ask questions. You're going to be, in this program for a few years, you're going to come across things that you aren't going to understand, and being the shy person in the corner, not asking, oh, I don't know how this works, it's not really going to help you. Instead, raise your hand, ask a question, ask ChatGPT, ask your professors, ask your roommate, whoever. Just try to get some information if you can, because it's the best way to learn. The second one I really put in here is talk to your professor. They know stuff, and they are experts. I literally come to this university. I love you guys are amazing, but I go talk to the professors, and when I talk to them about what are they researching, what are they doing, and they're doing phenomenally amazing things. So if you go talk to them during office hours and you learn a little bit about what they're working on, you will start to see oh gosh, this is so boring. Why would I care about aligning this in this particular way? Well, if you put that all the way to the end, now you can start to design these chips that we had designed up there. And the one that I was showing you, just a quick anecdote there, is one of my colleagues when I was in grad school. He came a couple of years after me. He finished, we both had the same advisor. I went off and joined ISI. He joined AMD as an intern, and he was given chips, and his job was to go test the chip. Okay, this works, this doesn't work. And then he was told, well, why doesn't it work? He's like, well, I don't know. Maybe you should go find out. So he'd go find out. Oh, you found out pretty well. And he kept working on that, working on that, working on that. And over the last 10 years, now he is the chief architect, and that was the chip that he designed. So, you have that ability if you're determined to go after it. But if you don't know to, give it a try, then you'll never make it. But yeah, going back to the professor one, the other part I try to tell people is if you ever want a job and I'm going to go talk to a professor and they're going to say, hey, I have these really great students, those are the ones I'm going to recommend to our recruiting staff. So again, talk to your professors. The third one is tinker with technology outside of your comfort zone. So if I put a lot of software stuff up here, a lot of things that probably aren't really maybe the core focus of this particular class, and it's because it is the hot, trendy topic. I mean, if you turn on the TV and it's not talking about AI or not talking about something going on with OpenAI or hopefully AMD, you need to be aware of what that technology is, how to use it. You can do simple things like go watch YouTube videos or go to GitHub and download projects and play with it, but you need to try it out. You need to do something. Don't just wait and think, oh, this is just a fad, it's just going to go away. It's definitely not. And then I like to say, time's on your side. I would trade places with you guys in a heartbeat. If it was like, hey, would you rather be in college right now doing something or do what I'm doing right now? Like, you have the world to your disposal. You have so much information at your fingertips. You have so many opportunities. You have time. Hopefully, you may have children. I have a child. It drains my attention and focus, whereas now you have time. Like, how many people here play video games? Fewer than I expected. I'm jealous about that. I don't play video games anymore. I wish I did because I just don't have as much time. So use the time that you have and really try to take some risks, try some different things. And then last one is, I love the topic of this, the title of this class, Change the World Chips. You have the ability to design, to build, to fabricate something new and novel that is going to literally change the world. We would not be where we're at now with AI if we didn't look back and think, hey, how should we change this computer architecture in order to get it to be really advanced? It started without high-performance computing, and we started to say, oh, we should put single precision and maybe double precision into our GPUs. And then we started thinking, well, if we have these really powerful compute units, could we do more with it? And it eventually evolved to us being able to do different AI and other computations. So I know I was kind of rushing through this kind of quickly, but I wanted to save time here at the end to be able to turn it over for questions. I do have two of my colleagues who are joining me that I was going to throw them under the bus and maybe ask them to answer some questions. So if you have any questions, I'll turn it over here and let you start. But thank you all for the time.
Thank you very much. Would you like to introduce yourself?
I was going to say, maybe if you get the microphone, do you want to just...
Absolutely. Now, the microphone doesn't help within the room, but it does help for the remote students and so on.
Gotcha. Okay. Hey, nice to meet you all. Scott Stankard, work for AMD in our client compute business. Specifically, I'm a product manager. So a product manager at AMD is somebody who works between our engineering team and the business team to help decide what products do we want to go make, how can I go make money on them, and then ultimately, how do I deliver to you all a great gaming processor or a great laptop or whatever it is that we're creating. So nice to meet you all, by the way. BSEE from Purdue, 1999, so it's awesome being back on campus.
My name is Anna Arnadova. I graduated this past May, so like 4 months ago. And I'm a product development engineer at AMD, so I get the actual silicon that comes from TSMC, and we create the test script to make sure that it works at a module level and you guys don't get defective chips and you get the quality that you deserve.
And we have one more colleague, Tiffany.
Sorry, I'm coming. You all probably have met me at some point, but Tiffany McKay, I'm on the university relations team and I'm a program manager.
Hey.
So this is kind of unrelated, but how did you know like you wanted to go from maybe like hardcore engineering to like product management or like that role?
Yeah, honestly, it took time, right? It was not when I graduated here. I did not say, "Oh, I got my engineering degree because I wanted to go do business things," right? Like, I had no idea at the time. But for me, it really was a very sort of individualized thing. As I progressed in my career, I just kept thinking ahead about like, where am I going to be 5 years from now? Where am I going to be 5 years after that? And at some point, I looked at sort of my future and decided, you know what, I'm really getting more and more interested in the business side of things. I started to discover I had skills around talking about technology and not just delivering the technology. And I saw opportunities to be able to sort of bridge that gap. And so I thought, all right, I'm going to go get my MBA. That's going to help give me the part of the education I needed on the business side to be able to talk with the business as well as still hang on to my engineering. So that's kind of how I approached it. And just I always wanted to keep my skills fresh, make sure I was always more marketable. I've been at AMD for 26 years, which is pretty unique in this industry, but not unique to AMD. There's a lot of people that have been there a long time. But I still wanted to continue to grow, continue to develop, and whether it's an MBA or something else, that's absolutely something you want to continue to do. Always make sure you're delivering on like what are the next set of skills that I need to learn. Now it's AI. I got to go figure out how to do all this, right? Like to Andrew's point, I'm very jealous of y'all because you have time to play with this right now, and you're coming out of school at a time when you will know things that I have no idea how to do, and it's a very unique opportunity for you guys. So be curious about that stuff. Keep diving in.
All right, this is a slightly more technical question, but so especially with your new Instinct accelerators, so I know that CUDA has been extremely prominent, and this is probably going to get better for like AMD's ROCm platforms with the new like Instinct accelerators. But what is the plan to get? I know PyTorch and a lot of libraries now have support for ROCm on Linux, but a lot of them still don't. What is like the plan for ROCm and the AMD like AI computing stack?
It's a great question. So a lot of it is just getting more developers and more people more access. To be fair, it's only been a few years that we've really had a lot of the ROCm development and really targeting these different Instinct and Radeon devices. So the large part of this is platform completion, having you all, the open source community, help us to refine and develop and implement these, and encouraging you all to have access. But a lot of it is, you need to have access to hardware. So, step one is you can't run on something you don't have. So we're trying to make that available. The university program, we're trying to go to the different departments and saying, like, how can we help? What can we donate so that you have access to it? The second one is training. So making sure that you have access to the resources to be able to learn how to even use ROCm and HIP and how to implement different designs. It's really not that actually fundamentally difficult to write in ROCm similarly to CUDA. I mean, it's just, you have HIP versus ROCm, the syntax isn't that complicated. You're right in that the underlying libraries that other people have written have been primarily developed for CUDA, but we're making really big strides and a huge push. I mean, we have entire teams that this is their number one charter is to help us catch up, and we're working really hard to do so.
Yeah, I maybe just add to that. I think that's great, and emphasizing like anytime there is somebody that's sort of locked into a certain software, you have to help them bridge out of that, and that's what Andrew was talking about with how we provide those tools to be able to get somebody out of that walled garden of CUDA and into a more open source ROCm environment. But I was going to add to that, over the last several years, AMD's made a number of sort of small but very strategic purchases of smaller companies that have a lot of programming talent. And so AMD historically was a hardware company. We're very much growing into a software company, acquiring all those skill sets that we need. And so strategically, that's how we're getting there.
Like if a student is looking to go into hardware software integration, what exactly are the skills that you want them to concentrate on? And
so for hardware software, at least at AMD, understanding how hardware works, that's kind of paramount and really fundamental. So, everything from can you write, RTL and understand how to design something, testing it, verifying it, making sure that it's functional in behavior. And then when you're thinking of where should this particular function run? Should it run on software and a CPU, on a GPU, on the NPU, or do I need custom silicon to do that? Being able to profile and analyze, what is the current state of that software? So a lot of what I would do early on would be just run profiling tools like gprof and just look at it and go, okay, 90% of the time I spent in this one subroutine. Okay, how can I make that faster? And are there hardware tricks to do that, or other mechanisms? So I mean, again, a lot of it is understanding, breaking that software down or that problem down into its smallest components, and then Amdahl's law, figuring out what can you accelerate the fastest to make it run. would be a good starting point.
Hi, I was just wondering, how does 3D Vcache work, and why does it provide such a benefit in performance?
You want to go for it?
Yeah, I'll talk about it specifically from a gaming perspective because that's where we see a lot of the uplift, right? So if you think about as you're playing a game, there's a lot of sort of random data fetches that you need to do. And that's typically you're going out to system memory to go get that. And that adds latency, right? And so ultimately, the CPU is going to get the data out of memory, and then it might do something to it, and then it feeds it to the graphics card. So sometimes that graphics card, even if you have a ton of horsepower, it's actually bound by just waiting for that data to come from memory. So, X3D, 3D Vcache is just a super large level 3 cache, right? So it's bigger. So now I have all, that much more data that I can keep right on the silicon, so I don't have to go out to memory. And so it doesn't help every game. Some games it helps a lot. Some games it helps, a moderate amount. Some games it's just a little bit. But it's all about having the data closer to where the compute is actually happening. And maybe building a bridge to the AI side, it's kind of a similar problem, different problem, but a similar type solution where you're trying to get the compute to the same place where the data actually is. And so you see us stacking up these huge caches to be able to hold these large models so that you can actually, operate on it in a way that normally would be much, much more slow if you had to go out to memory for it.
Maybe one more question, and then hopefully some of you can stick around a bit later, as in case students have another class.
For Dr. Schmidt specifically, you mentioned you had both a PhD and your master's in computer and electrical engineering.
Yep.
Which one would you recommend specifically for going into this industry? Does it favor one over the other?
It's a good question. I was limited because there was no computer engineering PhD when I was doing my PhD, so I got an electrical engineering degree. But I was really focused on computer engineering. To me, it was more analog, maybe putting it simply like analog versus digital. I like ones and zeros. I like determinism in that regard. This whole it's 1, it's 1.1, it's 1.2 terrifies me. So I shied away from that. There are other experts. Hopefully you all can solve those problems and do it. But a lot of it is, don't think that you're a computer engineer, you can only do computer engineering. I mean, you can do physics, you can do chemistry, you can do all sorts of different things. Yeah, good question.
Well, thank you very much, everyone. We really appreciate you taking the time to come and say hi.
Thanks, everybody. Appreciate it. Thank you.